Hey physics kids, Mrs. Campbell here. In our last video we talked about what causes pressure in ideal gas and the things we could do to change that. We're going to take it a step further today and look at pressure volume diagrams. So pressure volume diagrams show ideal gas processes. In an ideal gas processes we're going to have a fixed quantity of gas, so that N value in our PV equals nRT equation stays constant. And we'll have well-defined initial states of our gas in terms of pressure, volume, and temperature. So a PV diagram is just that. It's a graph of pressure versus volume. So pressure being on the y-axis and volume being on the x-axis. So what a pressure volume diagram tells us is it tells us about the state of a gas at any point in time. Now, of course, the diagram itself doesn't have to have the temperatures labeled on them, because if we know the pressure, we know the volume, and we know the number of moles of gas that we have, we can use the ideal gas law to calculate the temperature. So here actually is an example of a PV diagram with a process. When we look at an actual process on a diagram, we'll visualize it with these arrows that show us how the gas is changing over time. So let's talk about what those processes are. There are 4 different processes that you will need to be able to know and identify on a PV diagram. One is an isovolumetric process where volume doesn't change, iso meaning constant. There's isobaric processes where pressure doesn't change. Isothermal processes where, as you can guess, temperature doesn't change. And the last process is called an adiabatic process. In an adiabatic process, what happens is there is no heat transfer. So let's talk a little more detail about each of these processes and take a look at what they would look like on a PV diagram. So first of all, let's talk about an isovolumetric process. An example of an isovolumetric process is if I have a sealed container so the gas can't escape, and I raise the pressure without changing the volume. Well, how would we do that? Well, if you remember back to our last video, we talked about one way we can change pressure is to increase the temperature of a gas. So if we warm the cylinder, if I stick a Bunsen burner underneath it, then the molecules are going to be moving faster and they're going to collide more often with the walls of their container and they're going to exert more force. But the volume can't change because the cylinder is sealed, so this is isovolumetric. On a PV diagram, then, an isovolumetric process is a straight vertical line. So I start out, and this is a case where I am increasing the temperature of the chamber. I'm sticking that Bunsen burner underneath it because I increase the temperature of the gas, right? I get more collisions, so the pressure increases. Of course, I could also take this container and I could stick it in an ice bath, right? If that were the case, then my arrowhead on this pressure volume diagram would go in the reverse direction. So the pressure would decrease, but the volume would stay constant. So that's an isovolumetric process. Question for you. Let's say I increase the gas from 100 degrees Celsius to 200. So I double the Celsius temperature of the gas. How does the gas pressure increase? Well, if you said double, you're wrong. Remember that temperature has to be in Kelvin. So if I add 273 to both of these, it doesn't double. It goes up by 1.3. Did I trick you? Or did you get it right? All right, next process is an isobaric process. Remember I said that isobaric processes, the pressure will remain constant. Well, how do we achieve that in a gas? Well, one way we can achieve it is by using a container that has a piston, a movable piston in it. So what you can imagine, it's kind of like a lid that's inside the chamber, and the height of it will adjust based off the forces inside and outside. So a piston stops moving when the external force, which would be like the pressure from the atmosphere, is equal to the pressure inside, which is the pressure from the gas. So for example, if I stick this chamber under a Bunsen burner and I put energy in through heat, right, the temperature will go up and the molecules will start moving and they're going to exert more pressure. And as they exert more pressure, right, that chamber is going to rise, right, that lid is going to rise, And as the gas expands, right, remember pressure goes down. If I have more room to move around, I'm not going to hit the walls as frequently, right, which will decrease pressure. Remember that volume and pressure are inversely related. So if we think about what that looks like then on a PV diagram, in this case we are putting heat in, so we're adding energy to the gas, increasing its temperature, and on my PV graph that means that the volume is going to expand to try to keep the pressure constant. So I have a flat horizontal line on a PV diagram. Next process is an isothermal process, a constant temperature process. How would we do that? Well, if we took our cylinder of gas with a movable piston again, and we put it inside a water bath, a constant temperature water bath, or maybe it's an ice bath, and I either compress or I expand the gas. All right, if I squeeze the gas, remember we said if we decrease the volume of a gas, the molecules are going to hit the walls more frequently, and that's going to increase the pressure. So if I push this piston down and I compress the gas, we call that an isothermal compression, whereas if we expand the gas, we call that an isothermal expansion. Now, how does this look on a PV diagram? Well, if you remember from Puvnert, right, PV over T, pressure and volume are inversely related to each other. So when I put that on a graph, it's not like it's a straight slanted line. In fact, it's a hyperbola. So if we look at what that would look like here, in this case, this is a compression, a squeezing of the gas, right? The pressure is going to go up, but it's not a straight line. It has a nice little curve to it. Now, these curves actually have names. These are called isotherms. So anytime I am moving along an isotherm in a PV process, I do not change temperature. So if I don't change temperature, what does that mean about the kinetic energy of the gas? It must stay constant. All right, one more process to go. An adiabatic process. An adiabatic process is a process in which heat is not transferred. So in this case, heat, which is symbolized by a Q, is equal to 0. Well, how do you get heat not to transfer? I mean, all these processes so far, we were using the transfer of heat, which is the transfer of energy, in order to change pressure, volume, or temperature of the gas. So how do we do this? How do we have a process where we have no heat transfer? Well, for example, a good example of an adiabatic process is when a gas suddenly expands. Right, and that actually is how cloud formation happens. If you can think about what's happening here, right, as warm air rises, right, the air gets less dense, and all of a sudden, poof, right, huge expansion. And that results in a decrease in temperature, and it gets so cold, right, I get ice crystals forming. So what this looks like on a PV diagram is I have this expansion, right, so I have this increase in volume. And when volume increases, it's increasing as the pressure is decreasing, and I get this sudden drop in temperature. So I don't stay in an isotherm. It's not an isothermal process, but it looks kind of similar because it's curved, but it's dropping from one isotherm to another. So the temperature here is dropping. We could go the other direction. We could have this quick compression of a gas, and that raises the temperature of the gas. Now, I have a really great demo of this.
Come on, baby, light my fire. Come on, baby, light my fire. Try to set the night on fire.
Now, an adiabatic process, what's really interesting about an adiabatic process is we're changing the temperature of the gas or the kinetic energy of the gas, right? But without doing that through the flow of thermal energy, the flow of heat. So that must mean something else is changing the energy of the gas. And if you remember back to our first thermal presentation, we talked about how do you change the energy of a gas, we had two ways, right? We had heat and we had work. So if we're changing the energy of the gas, then, and we're not changing heat, we must be using work to change the temperature of the gas. We're going to talk more about work in our next video. All right, I have some questions for you. So I want you to pause this video and read the question and then see if you can answer the question. Well, in this case, we are adding heat to this chamber by lighting a fire underneath it, and up goes the piston, which means that the pressure must be trying to stay constant. So if you said isobaric, you are correct. How about this one? Pause the video, read the question, see if you get it right. Well, in this case, we are adding weight, so we are squeezing the chamber, which means we must be changing the volume. And if we're squeezing it, we must be changing the pressure too. So that doesn't give us a lot of choices, does it? So it's in a water bath, so we're going to say that this is isothermal. Again, read the question, pause the video. In this process, we have an isovolumetric process, right? The volume staying constant, pressure is increasing, and if pressure increases at constant volume, then the temperature must go up as well. Another way we can visualize this is if we think about what isotherms look like. Remember, isotherms were those curvy lines, and we are clearly moving off a curvy line. In fact, anytime we move away from the axes in any way like this, then we are going to be increasing the temperature of our gas. So if you said it was higher, you are correct. How about this one? Pause the video. Now, what type of process is this? This must be isobaric, right? We are squeezing the gas, but in a way that the pressure is staying constant. Well, if we're squeezing the gas and the pressure is constant, then we must be lowering the temperature of the gas so that we can slow down those collisions. And you can see that we are moving off an isotherm, we're moving towards the axes, which means the temperature must be going down. All right, how about this question? In this question, I have what's called a cyclic PV process. I first go through an isovolumetric process where I increase my pressure from PO to 2PO, so I double my pressure. Then I go through an isobaric process where I am increasing my volume 3 times its original, or from VO to 3VO. And then I go through another isovolumetric process where I decrease the pressure back to the original pressure, and in my final stage here, stage 4, I'm going back to my original state of the gas, so VO/PO. All right, my question for you is, what is the temperature at each point if we call this initial temperature TO? Pause the video and see if you can get the temperature right at each of these endpoints. Well, remember the ideal gas law, PV equals nRT, can be rearranged so that temperature is pressure times volume over number of moles times the gas constant. And these are staying constant, right? In an ideal gas process, or in our ISO process, the number of moles is staying constant. Of course, R is a constant. So to find the temperature, I just need to multiply my numbers together and compare it to my initial temperature. So we said that PO times VO is equal to TO. So if I double the pressure while keeping volume constant, then I have 2PO times VO, which gives me 2TO. And if we go over here, right now I have double the pressure, 2PO, but my volume is now 3VO. So 2 times 3 is 6. So if you said 6TO, you are correct. And in my final state here, I go down to the original pressure, so PO times 3VO, so 1 times 3 is 3TO. How'd you do? All right, last problem. So I have an ideal gas here, 1 mole of it, that is taken through this process. So process A to B, I decrease the pressure of the gas from 2.2 atmospheres to 1.4 atmospheres while keeping constant volume. And then I increase the volume, so it goes through this expansion where the volume goes from 6.8 times 10 to the negative third meters cubed to 10.7 times 10 to the negative third meters cubed. And when I get to state C, it says that the temperature actually reaches its original value. So this dotted line here must be an isotherm. So my first question for you is, what types of processes is A to B and B to C? My second question is, calculate the temperatures at points A, B, and C. So pause the video and see if you get it right. All right, so if we talk about types of processes, right, my first process, A to B here, I'm staying at constant volume. So if you said that this was an isovolumetric process, you are correct. And from B to C, right, we keep constant pressure. So if you said B to C was isobaric, then you're correct. Now, in order to find out my temperatures, I need to use Puvnert, the ideal gas law. I have 1 mole of gas, so we're going to use PV over 1 mole times the gas constant 8.31 to give us the temperature. Now, remember, you have to pay attention to units. What did I do to you with this problem? I changed units on you. So I'm fine for volume, right? I'm in meters cubed for volume, so that's cool. But notice that these are in atmosphere, so you have to change them to pascals. So make sure you multiply by 101,300. Now, if you did that correctly, you should get, for the temperature at A, which remember is the same as the temperature at C, you should have gotten 182 Kelvin. And then for point B, you go through the same process, you should have gotten 116 Kelvin. Does it make sense to you that the temperature is lower at B than it is at A or C? Well, hopefully, yes, right? You're below the AC isotherm. So if I'm moving this way through the axes, that must mean the temperature is decreasing. How'd you do? I'll see you in class.